Welcome everyone. My name is Ege Özgün. I'm an assistant professor at Hacettepe University, Department of Physics Engineering. I would like to first thank the organizers for giving me a chance to talk about my research at COVID-6. Today I will talk about quantum computing in Penrose Unilluminable room geometry. I will shortly refer to as the Penrose geometry. I would like to thank my colleagues for their contribution in this study, in this work. Now let me start by introducing the Penrose problem. So it first appeared in 1958. So Roger Penrose, together with his father, Lionel Penrose, asked the following question. So imagine a room covered with mirrors, a closed room. And if you lit a candle, can you find a place where the light from the candle cannot reach? Means that is not illuminated. And we can cast the same problem just in the following manner. Imagine you have a closed geometry, and when you hit a billiards ball, can you find a region where the billiards ball cannot reach? So these are two equivalent ways of asking the same question. And actually they also give the answer to the question. And so they suggested this geometry. You have an ellipse, and then you separate the ellipse into two halves, and then these points Q and R are the foci of the upper ellipse, let's say. And if you choose these regions, the region A and region B, in the way that they are below the line connecting the foci of the half ellipse, then this point A cannot illuminate B or vice versa. So this is the original solution. And this problem, in terms of just geometry, was also studied in different manners. And Klee asked the same question in the opposite way. He asked, is every polygonal region illuminable from some point, which actually is just the same problem, just Penrose with his father asked and solved. And Tokarsky came up with several different geometries consisting of multi-sided polygons. And here, in all these different geometries, the points A0 and A1 cannot illuminate each other. And this idea can also be formed in the way of the Bunimovich Mushroom idea. So here, as the points R1 prime and R2 prime goes to R1 and R2, then you obtain this Penrose geometry where this region below this foci line cannot illuminate this box region or vice versa. And Paul Castle just generalized this idea to obtain different, so to say, ways of Bunimovich mushrooms. And you can ask this question. So this original problem from 1950s, nearly, this is 7 decades old, but there are actually very few research ongoing on this geometry, apart from this geometrical interest. So one of the few groups working on this problem is Tokuda's group, and they are mainly interested in the cavity properties, the ray dynamics, and so on. So what we are interested in is mainly for this work is the quantum vault problem in Penrose geometry. So we said, okay, why don't we just put some quantum dots inside this geometry? And we choose this specific 7 points, 4 of them inside this box regions, 1 in the middle, and 2 in these upper and lower regions of the ellipses. So you can see in this table, so the left column is the quantum dot label, and the right one is with how many of the quantum dots that this specific quantum dot can interact directly in single, with just a single photon coupling. So as you can see, 5 and 6 can interact directly with 4 of the other quantum dots. And actually, this is coming from the restriction of the Penrose geometry. So you can think about actually 3 different regions. I will show the Lumerical simulations in a moment. So you can think starting in one of these box regions, or let me say, you can start illuminating your geometry from one of these regions. The second one is a region above the line connecting the foci of this half ellipse, a region here, but not inside the box. And another one is just the middle. Now, the important thing here is, okay, so this is the Lumerical simulations, and yes, we are not interested in the ray dynamics, but here we can restrict ourselves by choosing the correct wavelength and the correct dimensions for our geometry, such that the effects of wave dynamics here will not cause this idea to collapse. So we still, as you can see, this region is not illuminated when we start from the middle, or when we start from the top, these 2 boxes are not illuminated, or when we start from one of the box regions, it can only illuminate the other box, but nothing below this foci line. So here, this dimensions are on the orders of 10 to 20 microns, whereas the wavelength we chose was on the order of 5 to 600 nanometers in the visible range. So this is a perfect region for us to study, because the effects coming from wave dynamics will not cause this geometry to, collapse. So we are interested in this region. So we can also call this as just the ray optics limit. So we can safely state all the things we said for the Penrose geometry for our problem. Now, what we can do is we can just cast the equations for our system and solve them, but we have to be careful. So normally we can use the medium-assisted Maxwell equations, the green diodes, and since we are interested in the quantum walk problem, we need to use Heisenberg dynamics for the atom field interaction, and we can surely use dipole and rotating wave approximations. So we will end up with Jaynes-Cummings type equations. But if we do not consider the Penrose geometry, then we can have all the modes coming from all the bosonic modes coming from the cavity modes. But when we put the restriction of the Penrose geometry, we'll be limited with the modes. Actually, this geometry will give 5 of the bosonic modes. Now, for this work, we concentrate on the 3 of those. So I will show you in a moment the Hamiltonian we used. And the other 2 modes will not expected to change the general results we have. So the 3 modes we used are sufficient to capture the main properties of the system. So with these three modes, three bosonic modes, we can write a general Jaynes-Cummings type Hamiltonian. Here we have the bosonic modes. We have then the individual contribution of the 7 quantum dots, and then the atom-light coupling here. But surely we know that also in the table I showed in a moment, all quantum dots cannot directly couple to each other. So with the 3 different bosonic modes we chose here, this B1, B2, and B3 are the annihilation operators for these bosonic modes, whereas this dagger one is the creation operator. So here we can limit ourselves to these 3 couplings. And now I will show the results for the quantum walk with calculated with starting from this Hamiltonian. So first here, this I denotes the bosonic modes, the intensity of the first one. So we start from IA, which means we start from some mode at one of these boxes here, either this one or this one, it doesn't matter. So we start with a photonic mode, and we start with a single excitation. So you will see in a moment that when we start with a single excitation only, we will have this oscillation type of behaviors in these intensities. So this x-axis is the normalized time, and here we have the intensity, and you can see some oscillatory behavior. Now I will move to another bosonic mode. This time we are interested in a bosonic mode that starts here. So you can see the oscillatory behavior better here. And these IA, IB, and IC are, so IAs are the bosonic modes in these upper boxes. IC are the ones in the lower boxes, whereas IB is this middle region. So we can also, of course, start from one of the excited states of these 2-level systems, or the quantum dots. So here we start at an excited state of this first quantum dot, and then again we can see just how the bosonic modes changes in this sense. So for the single excitation, we still see the oscillatory behavior. Now we can also start from the excited state of this middle quantum dot, and again we have this oscillatory behavior, and finally we can start the excited state of this quantum dot, again the same overall behavior. Now the interesting thing happens when we have 2 excitations. For instance, you can think this as starting with 2 photons. So we have 2 excitations in this region, 2 bosonic modes in this region, and now we start to see the localization effects. So it never recovers. So we will never have this 2 excitation again. And we can also start from the bosonic mode at this middle region. It is again the localized behavior. Now I want to introduce the concept of global entanglements. One can calculate the global entanglement via the purity, and purity is defined as the trace of the square of the density matrix. So let's say I want to calculate the global entanglement of my bosonic modes. So I will calculate this for each of the bosonic modes, meaning that I want to calculate, I will trace out other degrees of freedom, and I will have this reduced density matrix for each bosonic modes. I will square them, take their trace, and calculate their purity. And then N is the number of constituents I'm interested in. So for the bosonic modes, there are 3 of those in our problem. So, and it's 3 here. I can calculate my global entanglement in that way. So now let's check the total excitations in terms of photonic and atomic modes. So the atomic modes are just the 2-level systems coming from the 2-level systems, the quantum dots, and photonic ones are just our bosonic modes. So for the single excitation, you can see this perfectly oscillatory behavior. And this also reflects in their global entanglement behavior. So this is perfectly consistent. And this is some sort of a sanity check for us. So when there is a single excitation, let's say a single photon, surely we will expect this interplay between atomic and photonic modes, because if we start with a photon, if one of the quantum dots just takes this photon and just goes to its excited state, then there is no photon. So when it emits the photon, then there is no atomic state. So this is purely very actually expected. But now when this is also same for starting from the middle bosonic mode. Now what happens if you have 2 excitations? Now again, we can see the signatures of this localized behavior. So this total photonic and atomic excitations, again, there is an interplay between them, but there is the oscillatory behavior is completely lost. The localization is now emphasized, and we can see that, okay, of course, this excitation does not, disappear. It's just now pronounced in the entanglement. As you can see, at the first instance, when we have this total intensity 2, we start with that, and then this localization behavior is also supported with this the results for the global entanglement in that sense. So these are, and this is for the case when we start from the middle mode. So these are our main results, and to sum up, by using the advantages of this Penrose geometry, it would be possible to use this in designing different, entanglement schemes, and also different ways of controlling the behaviors in quantum optics, the light matter interactions, and also in quantum computing. So now our future work we intend to do is first to generalize this to this all 5 bosonic modes, and then to investigate how, if we can, and if yes, how we can use these ideas in quantum transduction, and then to investigate this geometry with different dielectric regions for this Penrose geometry, for adding more tunability and control, and that way to find a way to achieve controlled way of achieving multipartite entanglement. So thank you very much for listening to my presentation.